let's then move to some examples to predict failure for various problems. So let's just step into that and kind of learn together. Here you have a thin wall, and this thin wall pressure vessel has a radius of 20 millimeter, a thickness of 1 millimeter, and it is subjected to 5 megapascals. For some particular reason, you have some sort of tube that needs to be created that goes through this hole. And we know we're given that the yield stress of the material is 250 megapascals. And the question is determine if there will be a failure at this hole, which is 1 millimeter radius, uh, and to use the maximum principal stress. So to do this problem, the first step is to realize that the maximum principal stresses can be easily calculated for a pressure vessel without a hole. The stresses are very simple. The axial stress is PR over 2T, which is in the x direction. The hoop stress is PR over T, which is circumferential direction. And so what we want to do is to use the maximum principal stress criterion and then determine if failure occurs. So if I know that the far field stress here in this hoop stress in the y direction is PR over T, and in the x direction I have PR over 2T, we know this hole is going to introduce an additional stress state. And that stress state is coming from the stress concentrations of that hole itself. Then what I can do is remember and remind ourselves that we studied what the hole can do to a structure that has a far field stress. The far field stress is sigma naught. And then what I can do is I can notice here that this stress state is 3 times down the far field stress. We learned that in a stress concentration lecture. We also learned that the stress right here, right about there, aligned with the loadings applied at theta equals 0. That stress right there, in the hoop direction, so in the y direction, but at this point, that stress right there is the negative of this load applied. So we can use superposition because this equation or this plot or this configuration is for a load applied axially. And our situation is a multi-axial stress state where we know the loading in 2 different directions. In one direction is PR over 2T, which is axial, and PR over T, which is hoop. So let's try to apply that concept. And what I did, I broke it up into 2 problems. I studied the situation of the axial stress state. Again, let me remind you what's going on here. In this direction, you have PR over T. In this direction, I have PR over 2T. And then PR over T is shown here. So I broke up the problem into two, and then I'll use superposition. So let's look at this carefully. If I look at the stress state right here, when I apply this axial stress right here, which is this one right here, sorry about that, I get that at point B, which is right here. I'm looking at this point right here. Let's look at point B. Point B, the stress state is going to be PR over 2T times 3. And then if I look at point B, but I look at it here, you can see that at point B, the stress states are subtracted now because that's a compression stress that occurs, and it's going to be the negative of PR over T. So you can do the calculation here twice, and that'll give me PR over 2T. And then you can repeat the process at point A. I'm not going to do it now, but you can add them by superposition. You can see here that at point B, I got exactly what I said, PR over 2T. We can then try point A together. Point A, you can see that the stress state axially at point A, this stress axially causes a compression stress in this direction. And that amount is PR over 2T, but the negative value. And then you have this one here, which is sigma theta. And that sigma theta causes at point A, it causes 3 times, so plus 3 times PR over T. So I will have to multiply the top by 2 and the bottom by 2, so I can add them up. And I get 5 PR over 2T. So at point A, I got 5 times PR over 2T. Well, at point B, I got PR over 2T. And you can see here, that is exactly what I got. So I was able to find the stress at point A, which is 5 PR over 2T. And I found the stress at point B, which is PR over 2T. And then what you can do in this problem is I know the pressure, I know the radius, I know the thickness for point A and point B. And I'll compare that to the sigma yield. And it turns out that this stress right here is greater than sigma yield. So it fails that criteria. At point B, you find that it is below the criteria, so you're good to go. And you can see that we did that here. It was given to you, the yield. Everything else was given to you. So pretty straightforward there. Let's step to example problem number 2. This problem I had also discussed in the lectures earlier in time. And what this is asking for is to use stress criteria to predict failure of this very problem I had given previously. But this is now a brass wrapped on a steel. And the question we want to ask ourselves, and they give the yield value for each of these materials. And then it's asking you, hey, use stress criteria to predict failure. Pressure is not known between the interface, but they tell you that the pressure follows this form of P equals C, the constant C times some delta. And it's telling me that at 0.02 millimeters, 0.02 millimeters, the pressure is 9 megapascals. So you can actually calculate C from there. So let's do that. So P equals C times delta. Delta is 0.02. Pressure is 9.0. So if you divide this, you get 450. And so since the problem statement tells you that I want to look at the shrink allowance to be 0.1, you can now plug in that into the P equals C times delta equation. Delta is 0.1. I calculated C from this equation is 450. So the pressure must be 45 megapascals. So what I'll do then is study the problem a little bit more. Now we know the interface pressure to be 45. I'll first look at the brass. So the pressure here in this boundary is 45, according to the problem statement. I can use the equations for a cylinder under external and internal pressure applied. It turns out that there's only internal pressure applied here of 45. I can plug in all these numbers because I have the radii for the different geometric factors. And you find that sigma r at r equals a, which is right here at this boundary, is minus 45. And then that's a radial stress in the radial direction. Sigma theta, though, is in the hoop direction, and you find 88.6. So the principal stresses are just 88.6, and then sigma 2 is minus 45. So the max shear value then becomes 88 minus 45, which is 133.6. That's lower than 240, so no failure is predicted. I'll then examine the steel shaft, the one that's wrapped by the brass. Here the inner radii is 0 because it's a solid cylinder. So A is 0 there, no worries, A is 0. So all you get is that, and if A is 0, then B cancels out. And so the stress becomes sigma R becomes minus P, and sigma theta becomes minus P. I know that the interface pressure is 45, so therefore you get the pressure is 45. And then when you apply the criterion here, you see here quickly that no failure occurs because sigma max is less than it's 45 and it's less than 560. So no concerns there. Pretty straightforward. We're gonna study a pressure vessel. So it's a thin wall pressure vessel that's subjected to, now these are fatigue problem. The previous two problems were not fatigue. The two previous problems were strength related. This problem here, the next couple of problems is looking at fatigue. We're going to subject the structure to cyclic internal pressure P. And we're going to range that pressure from 2 to 6. And we're going to use Soderberg relationship. We're going to use the SN curve given below and use a factor safety of 1 to determine the fatigue life for two cases, R over T equals 70, the radius to thickness 70, and the radius to thickness 45, the radius of the thin wall pressure vessel compared to the thickness of the wall. They provide us with sigma yield is 350, so that's this number here at 1,000 cycles, and the endurance limit is assumed to be sigma yield divided by 2 at 10 to the 7 cycles. We'll get started then. And this stress strain curve most likely is true for true reversal. What that means is that if I choose a value here, say 20, that 20 megapascals is going to be the alternating stress. So when I look at the pressure vessel is going to have two stress states. One is the axial load and the hoop load. The axial stress is P, the pressure, times the radius divided by 2I is the thickness, while sigma 2 is going to be PR divided by T, where that's the hoop stress. I know the pressure is 6 or 2, so the minimum and maximum. The strategy will be to use Soderberg failure criteria, where sigma critical equals all this. But for sigma A and sigma minimum, I'm going to use the multi-axial stress state equation because that allows me to combine multiple stress states. You can see here that we can find the alternate stress and mean stress. So I have sigma 1A is PA times R divided by 2T. So that's what I get for sigma 1A. That's for stress state number 1, the axial stress state. The minimum stress state, the mean stress state, that's the alternating. The mean stress state is Pm divided by times R divided by 2T. P max plus P min divided by 2. That's how you do the minimum. Not the minimum, sorry, the mean. And that gives me that sigma 1m equals 2R divided by T. I can also repeat now that for the second stress state, which is the hoop stress. Pressure, alternating pressure times R divided by T. Plug that into this formula to get that you have 2R over T. And for the mean stress, you get 4R over T. Now I can calculate the equivalent alternating stress, and when you do, you get the square root of 3 times R over T. And the equivalent mean stress becomes 2 times square root of 3 times R over T. So now I can use Soderberg criteria, which is the formula provided here. And you can see here that when I plug in these numbers here, I can solve for sigma critical. And when I solve for sigma critical, I get 394.7 megapascals. Remember, the sigma yield is 350. The sigma mean was calculated as 2I square root of 3 times 70. And sigma alternating is square root of 3 times 70, which is this number here. And solve for sigma critical gives you 394, which is greater than the sigma yield, meaning that for a radius divided by thickness of 70, you're likely to fail through yielding. However, an R over T of 45 plugged in here gives you a sigma critical 140, and that will never fail at the first cycle because 140 is much less than, well, it's not much less, but it's less than 175. That's how you tackle that. You can actually find the number of cycles to failure due to this 140.53. That's already a combined case or combined loading condition. So you can actually go back here, use this curve to predict when you have the number of cycles to failure. But first you have to define this line using the equations we discussed before. And I have a few more examples here, I think. Yeah, I have this example, which I think is a good one. This example is a shaft that's subjected to a cyclic bending moment that oscillates between 0 and m, and the cyclic axial torque that oscillates between 0 and 2m, where m is provided to you as 200 newtons per meter. The SN curve is defined by sigma yield of 1,000 at 10 cycles, and the endurance limit, just a second, please. Okay. And so they want us to then sketch the SN curve. They want us to determine the radius of this shaft, so for infinite fatigue life. And then given this value of R from here, determine the life of the shaft if this moment that we have of 200 is increased to 250. So let's tackle this problem. Very interesting problem. I think very practical. Drawing the SN curve is easy. They give us the yield strength at 10 cycles. So that's 1,000 here and 10 here. That's just that point can be drawn. They give us the endurance limit of 500, which is the endurance limit means that any alternate stress below that should not cause failure. But they give us this point, 500 at 10 to the 7th. That describes this line. And they also told us that the moment varies from 0 to m, while the shear varies from 0 to 2m. So they're asking us to find R for a shaft for infinite life. We know the SN curve now. We can use the Soderberg relationship that looks like this. And what we're going to do, we're going to replace, to determine when you get infinite life, you can replace sigma critical with sigma endurance. So that's what we're going to do now. Plug that in instead. But the first step is that we have a multi-axis stress state because we have the moment and then we have the torsion. So we will use the general formula to calculate the equivalent alternating load, and then we get the equivalent mean load. So first, let's look at bending. Bending is provided to you, and bending is moment times the radius divided by moment of inertia. When you do all this calculation, you get 4 times m divided by pi r cubed. We also said the minimum moment per the problem statement, it varies from 0 to m. So therefore, the minimum stress is 0. Okay, so I have these two. And then I will take and calculate alternate stress. The alternate stress is 4m pi r cubed minus this minimum value divided by 2. And then I have sigma xm, which is equal to sigma maximum plus sigma minimum divided by 2. And that's a straightforward calculation. When you do these two calculations, you find that the alternate stress and the mean stress both are equal to 2m divided by pi r cubed. So very simple here. In this case, the alternate stress and mean stress combine or match, but that's not always the case. So from torsion for the, and these only the axial stress, right, caused by bending moment. So that's the sigma XA and sigma XM is what goes into this that, so it goes there and there. It goes here and here. Now I have to calculate shear stress state. The shear stress state for torsion, you know that you have the torque times the radius divided by polar moment or inertia. R is the basically radius of that shaft. We were told that the torque is twice m, so that, and we know that the cross section circular, so that's pi to the r4 divided by 2. This gives me 4m divided by pi r cubed, and the minimum shear is 0. So in reality, I cannot calculate the alternating stress and the mean stress using this formula, but because the minimum shear is 0, these two are equal to each other, and it's going to be equal to twice m divided by pi r cubed. So both bending and torsion both have the same value actually in this particular problem statement. So now we can calculate equivalent mean and alternating stress. Remember, what we're going to do is plug this here into these equations, and I'm able to then find that the equivalent axial and equivalent, the equivalent alternating and the equivalent mean stress is equal to each other actually, and it's 4m divided by pi r cubed. I invite you to try that at home. To calculate infinite life, what we'll do, we're going to plug in the sigma endurance in here, where sigma critical shows up. And then we're going to plug in the equivalent values for alternating stress and mean stress. Both are shown here. And what I'll do then is solve for R from this equation. I know sigma critical, or when sigma endurance is, that's 500. And then the sigma yield is 1,000. And I know those values from the problem statement. It says sigma yield is 1,000 and sigma endurance is 500. That's what that came from. It's 500 and 1,000. The radius becomes 9.141, so you can have infinite life. But it says that if you use this value to now redo the problem, but increasing the moment to 250. So we're going to use the Soderberg criteria, plug in the equivalent value of alternating stress, which is 4m divided by pi r cubed, divided by 1 minus the mean stress of that's equivalent, 4m divided by pi r cubed. The yield is 1,000. And so all this calculation using that radius gives me 714.92. Given that number now, what I'll do is use this curve visually, 792, and then calculate number of cycles to failure. That's one approach. Second approach is just to use this equation here, where you know all these values. You know that's 1,000. We know sigma critical is 714 from this right here. Divided by 1,000, the fatigue strength is 1,000 minus 500, which is the endurance limit, which is that number. I know the number of cycles to failure for endurance is 10 to the 7. They give it to us, and the fatigue strength is 10. So therefore, when I redo all this calculation, get the number of cycles to failure is 2.6 times 10 to the 4. Any questions on that problem statement?